Thank you. Okay. Afternoon, everyone. Welcome to my update on the current projects that we are running at PHYLA. So I'm not sure if every one of you have heard of PHYLA or have been to PHYLA, so I'm just going to give you a little bit of background. PHYLA stands for Phytosanitary Research Laboratory or Facility that was constructed through funding by Hordgrove. So it's specifically targeted at phytosanitary research, which is critical for market access and market sustainability. So within this facility, we aim to look at developing new treatments or look at old treatments to determine the viability of using them currently, especially when you look at insect mortality versus fruit quality. So the idea is to find a treatment that you can kill the insect while maintaining fruit quality. So with the versatile infrastructure that we have at PHYLA, we are also able to upscale a lot quicker. So from small desiccator or container trials, once we have a treatment that works, we can upscale it to cold room and even a shipping container trial, all within this one facility, which is pretty amazing. So just to give you some insight into the toys I have. So we have 4 cold rooms. They all have been modified so that I can control the atmosphere inside. So we have a nitrogen generator on site. One of the cold rooms we've modified so that it's a fumigation cold room. So it has spark-proof fans, spark-proof lights, and a bunch of other things so that we can adhere to government guidelines with regards to fumigation. Last week, we actually installed my ozone generating and ethylene monitoring system. So we're busy testing that at the moment. So with systems like that, we're always expanding the capabilities of the facility and increasing the tools available for us to do phytosanitary research with. So with this idea of PHYLA, the vision is to have an integrated approach where we can look at insect mortality and fruit quality simultaneously. And because of that, the insectary to me is a cornerstone of that, because without the insectary, we can't make that happen. Field collecting the insects in the numbers and in the quality we need is not viable. So we have an insectary on site that is critical to everything we do. At the moment, Hordgrove has spent a lot of money ensuring that it's a very high class and a high-tech facility. We recently added an additional room where I can store fruit that we've inoculated with a specific size insect, so we can store them at ambient. They can then reach the stage that we need for further trials without interfering or without contamination from the other insectary side. And then we also have a fruit evaluation lab where we are able to determine if the treatment that we applied has any effect on quality parameters such as the firmness, the color, sugars, acids, that kind of thing. So we can do all of that in-house. So once again, QC on the side of fruit and insect quality is critical to make sure that the treatment we develop is feasible going into industry. So the colonies we currently have on site include false codling moth, banded fruit weevils, mayfly, and red spider mites. And as I said before, it's critical to have the numbers and the quality we need for the trials. So having colonies like these on site makes our lives a lot easier, as this is the critical part of having that integrated approach actually working for us. So the projects we currently have running at PHYLA consist of temperature trials and fumigation trials. So for temperature trials, we have cold sterilization trials. We'll be looking at ozone fumigation, specifically on pome fruit, and then we'll also be looking at ultra-low with and without nitric oxide fumigation. So nitric oxide is a new fumigant that people are looking at, but you need to use it under an ultra-low environment, so it was perfect to align those two in one project. And then last but not least, this is a project that I'm very excited about, is incorporating ethyl formate into a polymer so that you can release ethyl formate and potentially then control your target pest or use it as an antimicrobial agent. So for the cold sterilization trials, we're going to examine insect mortality and fruit quality when we are storing at different temperatures for different durations. So at the moment, we are using wireless probes that I've got from Gas at Site. So they measure pulp temperature and ambient temperature every 5 minutes. They are super easy and super amazing to use. I have an app on my phone where I can look at the live feeds. If there's anything wrong with the probes, I get alerts. Pulling off the data onto Excel is also super easy. So it's not like an I button that you put in and you pray it didn't fail. So yeah, this is just a system I'm using at the moment. So there's just an example of what the probes look like with a snapshot of an Excel sheet that has your data points allocated there. And then the graph is just to illustrate what we could see when a room was set at 1.1 degrees, just measuring ambient. So measuring ambient for, I think it was over 6 or 7 days, we could see that the average temperature over that time was about 1.14, so the deviation over time wasn't that big. And then this is just an example of the ambient and pulp temperature in another room, which was set to 2.2. There, once again, the average temperature for that duration for ambient was about 2.18, and for the pulp temperature, it averaged at about 2.31 with a deviation of 0.11. So these deviations at least fall within the minimum guidelines that we should follow. So this has been a huge learning curve just for myself, not only on the inoculation and fruit quality side, but on learning how to interpret all the temperature data that has to align with all those projects. So for ozone, with ozone fumigation, we're going to be looking at its ability to weaken and rupture cell membranes. So in the USA, they use it to control mold and fungi, and they've also used it to control what they call a western black widow spider on table grapes. So for this project, I will be looking at its ability to control post-harvest pathogens, like, for example, stem end mold in pears. I will also be looking at its ability to control external pests. And then we'll be looking at its sanitation properties. So how can it either decrease the spore load or completely sanitize bins, fruit, or lugs, any surface area that fruit comes into contact with. So the images, it's just an example of what the ozone dosing and analyzing units look like. They've already been mounted at the facility, so I couldn't take nicer pictures before this presentation. But we will be using that system in combination with what we call a central composite design. So with that design, I'll be running different permeations of concentrations and durations to see what would be the perfect fit to control a specific insect or a specific pathogen. So instead of doing 110 experiments, I'll get a statistical model that'll help me move in the right direction. For the ultra-low oxygen, with and without nitric oxide, we will be looking at a pretty much hypoxic environment where you can try and control the insect. By adding nitric oxide, we will then have penetrating powers, so we can then try and see if we can control insects in fruit. So with this system, we will be using initially just sealed, vacuum-sealed containers. I'll show you now an image of the system we have where we can control the atmosphere or the gases that you put inside. You can then close this up, either store it at ambient, or you can place it into a cold room, which will then add another level of stress to see if you can find a treatment that would work. So this is just the objectives of the whole project where with ultra low we want to look at external insects. If there's a treatment that works, then we can overlay that with fruit quality and see if it has any effect. Looking at ultra low in combination with nitric oxide, I want to look at various internal and external insects, and then overlay that again with fruit quality to see if there's a treatment that would be feasible. So this is just an example of the system we had built. So with this system, I can set and control the atmosphere that goes into each container. We then seal them up, and they are gas tight. So we've tested them quite a bit. So they're gas tight. You can close them up, and you can leave them for what duration your treatment trial plan indicated. So for this unit, we just need to make some small modifications for nitric oxide, as we need to vent nitric oxide a bit more safely. So we'll just have to tweak the system a little bit. So currently, we are doing only ultra-low oxygen trials with a couple of insects. We're looking at mealybugs, red spider mites, grain chinch bug, and banded fruit weevil. So I'm not going to show you all the data, but I'm going to focus on my favorite, the grain chinch bug, since I'm always working on grain chinch bug. These are just like prelim results, but as you can see, as the oxygen percentage decreases, there's an increase in mortality. And we found if we included, for example, CO2 in combination with 1.1% oxygen, we could increase mortality up to 94%. So this is where the model comes in very handy, where it can show you which direction you can move in to get 100% mortality with the parameters you've set. So the last but not least, this is one I'm very, very excited about. It's the development of a polymer to release ethyl formate. So I'm not going to discuss a lot of this as it's going to be the next presentation. But this is sort of an accumulation of the last couple of years, the work that we've been doing with regards to ethyl formate and its potential to control target pests, as well as the antimicrobial properties thereof. So just like to thank everyone involved in this facility and amazing projects.